Hi everybody, and welcome to this lecture called How to Code Synthesizeable RTL. I'm Professor Adam Teman of the EnICS Labs at Bar-Ilan University, and I created this short lecture as a supplement to my digital VLSI Design course based on feedback I got from students who tend to make mistakes when they're first starting to write RTL. But this lecture can also stand alone for somebody who's just learning how to code. So just as a reminder, what is RTL? RTL stands for Register Transfer Logic. In other words, it is a description of a sequential design that passes data between registers, possibly applying some logic to the data on the way. So in my course, I show this type of a picture many times, and this is kind of how I would describe a sequential design in a microcosm. So basically what we have here is a pair of flip-flops, positive edge triggered flip-flops in this case, that are connected to a common clock signal and a blob of logic in between. What happens is when the clock signal rises, we take the value that's at the input to this flip-flop, I call it here next A, and we pass it over to the output of that flip-flop. That's called sampling the data, and the A value is now driven into this blob of logic, and we put some sort of a Boolean function onto this value A until it arrives at the output of this logic function, which I call here next B. On the rise of the next clock edge, we sample next B, and it is driven to the output of this flip-flop. Everything in a digital sequential design can be really broken down into paths of this type. RTL is the synthesizable subset of a hardware description language. Hardware description languages, or HDLs, which examples of such are Verilog, VHDL, and System Verilog, are usually Turing-complete programming languages. In other words, they really can do it all. It's a full language just like C or any other. But not everything can be implemented in hardware. Remember that we have to take whatever we write in our HDL and turn it into logic gates that can be implemented on a digital chip or an FPGA, etc. Therefore, only a subset of this, of the entire hardware description language, is considered synthesizable. We can only take a subset of this language and turn it from, the high-level language into logic gates. This is the synthesizable code, or this is also called RTL. However, RTL coding is not straightforward. We tend to, as veteran logic designers, not understand why it's so complicated because it seems really simple. But noobs, they just can't get it right until the coin finally drops. In this lecture is to try and help you get it right, despite your intuition, which is going to make you kind of take into our regular programming practices of a regular programming language like C or Python or so forth, which doesn't exactly work in RTL coding. So I've actually broken this down into what I call the Unforgiveable Rules. So taking inspiration from J.K. Rowling, there are 3 rules. The first one is never put logic on reset or on the clock. This is the Imperia rule. Never mix reset types, never create clock domain crossings. The second rule, the Crucio rule, is do not infer latches. Every if has an else, use full case statements, LHS for every signal for each condition. Okay, and the third, the worst of all, is the Avada Kedavra rule. Assignment always blocks. We have combinational, which are always at star. They use blocking assignments. Sequential, always at posage, use non-blocking assignments. And we always have to separate sequential and combinational logic and never assign a signal, in other words, an LHS, a left-hand side, from more than one always block. So that was just a really quick overview of what I'm going to be discussing for the next few minutes. So let's start with the Imperio rule, or curse. Okay, the Imperio rule, again, is no logic on reset, and I wrote on clock as well, but basically we're talking about reset is the common mistake that people make. Okay, reset and clock signals are not just any signal. They need to really be handled with care. There are most important signals and there are most unique signals in our design. Okay, so clocked signals should only be used to clock registers or other types of clocked pins and clocked macros. Reset signals should only be used to reset registers or other type of macros. Okay, so clocks and resets should not be used for other things. However, when we look at standard logic, we have what is known as a glitch. A glitch is a characteristic. It is not a design area. So I just took a combinatorial path over here where I have an AND gate. And the AND gate has, from its 2 inputs, 2 different logic paths that are coming into them. And I just, for the example, showed here buffers. This is a really short path, and this is a really long path in delay. So there might be a bunch of logic levels before it, and this may have a few logic levels. And let's say we started at the 0, 1 state, and 0, 1 going into this AND gate. We have 0, 1 at the after these buffers, because these buffers in the illustration are not changing the logic. We get a 0 at the output. And that's what an AND gate does. But now, during the next clock cycle or whatever, we toggle these two nets. So 0 changes to 1 and 1 changes to 0. And that's fine, but the 0 changing to 1 propagates really quickly over to here. And at that point, we have a 1 on this net, and we still have the 1 that's still on this other net because the other logic hasn't arrived yet. So when we have 1, 1 in an AND gate, what we're going to do is have our output rise. Unfortunately, a bit later, this net over here is going to fall down to a 0, and it's going to settle at 0. And then our net at the output will fall again. This is a glitch. Is it a bad glitch? Well, it wastes some power, but based on our static timing analysis, we're going to make sure that this glitch is not latched or sampled at the end of a timing path. So it's not an error. It's something that happens. In fact, it happens all the time. Okay? However, a glitch on a clock or reset signal is catastrophic. If we have a glitch on the clock, we're going to have an unwanted and unexpected data sampling. It's going to ruin everything. A glitch on the reset is going to cause flops to reset accidentally, thereby ruining everything. Therefore, do not put logic on reset or clock signals. In other words, if you write something like this, assign something equals A and reset, no, that's a no-no. Or always at star, case state, and we put reset over here in the right-hand side, no, that's a no-no. I'm not saying that these rules are not ever to be used. Sometimes you're going to do it, but that's only when you're a more advanced coder and not at the beginning. In general, never put any logic on reset or clock signals, or never do any of the things that I say not to do in these next few slides. So to emphasize the imperial rule, I'm going to give you an example over here. So a no-no that can easily be overlooked, but it actually is logic on reset. We're going to assume now that we have an input that we want to sample at the beginning of the process. So this is something that often happens. We have some sort of input to our design that we want to sample it before it changes, and then make sure that we are controlling this flip-flop that's holding it and not lose this initial value that we had. Okay, so the intuitive way to do this that is very wrong would be something like this. We have this input called in, and we'll call this reg in sampled. So this is going to be the value that we're going to sample when our input is going to come in. So always at pos edge clock or neg edge reset. If on reset, what are we going to do? We're going to save into in sampled. However, that's really bad. Remember that this type of a thing is going to have to map to a flip-flop from the standard cell library. And flip-flops from the standard cell library have set and reset values, which will initialize them to 0 or to 1. However, this in here is a non-constant value. So if we're initializing, if we're resetting this register here to a non-constant value, how is that going to be done? The synthesizer is going to have to decide to create a set or a reset signal during reset, depending on its value. This is logic on reset. It's going to need all kinds of muxes and so forth to put on the reset. So therefore, it is something that we do not do. It is a no-no. Okay, how would we do this then? Well, we'll create a state that's just used for initialization. So something like this. So always at pos edge clock or neg edge reset. If not reset, we're going to initialize our state into init, which is a constant. Okay, and then state is going to be next state on all other cases. We're also going to initialize this in sampled value to some value that's a constant. In this case, just 0. But then we're going to set for every other operation, we're going to set the in sample to be whatever its next state is supposed to be in, next in. Okay, then we're going to have an always at star over here. And if we're in the init state, what we're going to do is we're going to put next in is going to get this this input over here, right? And next state is going to get start. So on the first, clock cycle, what we're going to do is we're going to set into in sampled, and then state is going to go into start, and then we'll keep on doing our process while we already have saved the value of in at that beginning position right after reset into our in sampled type of a flop. Okay, the other part of the imperial curse is no clock domain crossings. So this is something that's not going to happen to you in initial RTL type of coding, but once you get to more complex systems, you're going to have more than one clock. So if we have these two clocks, clock 1 and clock 2, that come from a different source, maybe run at a different frequency. Anyway, as long as we don't know anything about their source and where it comes from, what their phase is and so forth, these clocks are asynchronous, and we cannot have any paths that run between them. Asynchronous paths, well, we will always have to assume that there's a worst case phase. That means that, the launching edge type of a thing came, and then just a picosecond later, the capture edge rose. We have to assume that, and so therefore we cannot actually pass data between two different clocks without special things that we call clock domain crossing approaches. So what you're never going to do is something like this. Okay, always at pause edge clock 1, A gets next A, always at pause edge clock 2, B gets next B, and always at star next B equals A. What that's going to do is that it's going to, this over here is going to create this flip-flop where next A is going to go to A when clock 1 rises. This block over here is going to create this flip-flop where next B goes to B when clock 2 rises, and next B is the output of a combinatorial block that is driven by A, which is on this clock domain. So A is a result of clock 1 rising, whereas, and therefore something downstream from it is affected by clock 1. Okay, and therefore next B has something to do with clock 1 in it. It may also have to do with clock 2, but that's even worse. Okay, but then clock 2 now is going to sample next B, which is really bad because it's affected by clock 1. So this is a clock domain crossing, and this is something we are not allowed to do. We cannot do without special handling. Okay, our next rule is called the Crucio curse, right? No latch inference. The only way to remember a value is with a register. In other words, using a flip-flop or a latch. If we accidentally ask to remember a value, a latch will be inferred. And we don't want to accidentally remember a value. We want to remember a value on purpose. When will it happen? Well, it's done when we do not assign a left-hand side, we do not assign for all conditions. Assigning is also called a left-hand side. So if we have something like this, always at star, case state is a right-hand side type of a variable. So what we have here is in the if state was start, we're going to put on the left-hand side next state over here, and it's going to get some value. But if our case was finish, then on the left-hand side, we have next state, which is fine, but we also have finished on the left-hand side. So the question is, what happened to finish if we were in the start state? And the answer is, we don't know, so we better remember the value that was there before. So the synthesizer will infer a latch that will store the value of finished if the case is start. And that's something that we didn't intend to do. Okay, so when are we going to have this type of a thing? First of all, it's going to happen if we have a combinational if without an else. So if we have an if and we don't provide an else, then if we get to the else state, if we don't abide to the if condition, then what are we going to have to do? We're going to have to keep the previous state of whatever was on the left-hand side, and that means we need to store it with a latch. Okay, a missing case option and no default. So what if we have some sort of a case option that doesn't appear here and no default? Then if we get to that case state, then we're going to have to put latches to remember what the values that are on the left-hand side inside the cases are. And if we have an if, else, or a case without assignment to all left-hand side signals, so that's basically what I showed you over here. So these are the three common cases of not assigning for all conditions. Okay, for all of the above, we have to keep the value of the non-defined condition, and this is going to cause latch inference. Okay, a similar problem is a missing signal in the sensitivity list. It doesn't cause exactly a latch, and simulators and synthesizers will handle it differently. But basically, let's say we have a 3-input NAND, and we only put A and B in the sensitivity list. Then what happens if C comes? And we're basically telling the tool, don't change the output when C changes. Usually synthesizers will just not pay attention to it because they know that it cannot map to a standard cell, but the simulator will adhere to it, and then we'll get differences between our RTL and our gate level that comes out of it. So just use always at star, and this will never happen to you. So to show you how to work around some of this Crucio type of a rule, okay, if we don't want to have latch inference, a really good practice is to assign default values for all combinatorial assignments. So at the beginning of an always at star block, assign all left-hand side values to a default value and override the default value if necessary with the following if, else, and case conditions. So for example, if we have always at star here, start with a begin, and then right away say we're going to assign, next A, next B, and next C, give them some sort of default value. That way, these are going to have a default value. We don't have to now put in every state here in the case or in every branch of the if else, we don't have to have an assignment to all three of these values. Okay, so we can have state 1 assigns next A, state 2 assigns next B, and state 3 assigns next C. But if we get to state 3, next A and next B, they will have a value, which will be 0 and 1. We don't have to worry about any latch inference. So that's a really good type of a practice. Just as a similar type of a good practice, it's a good practice to provide flip-flops with a reset value. So usually try to use, an always at positive clock or a negative reset. When you're a bit more, veteran, you can see that some flip-flops don't need a reset. You may be able to save some area and power with that, but really, at first at least, it's good practice to provide all flip-flops with a reset value. So we've discussed our two first unforgivable rules, and our third unforgivable rule or curse is the Avada Kedavra curse, right? And this is sequential combinational separation, okay? And this is important, and I've gotten to the point where this is the biggest problem with most new RTL designers. They cannot figure this thing out. So listen here now and don't do this. I equated it to the killing curse, Avada Kedavra. So if you go into Google and you search for different types of things, how to write them in RTL, they won't follow this guideline. Why? Because people put a lot of bad stuff, on the internet and don't think about it. I hope I am not one of those. But I promise you that if you don't follow this guideline, you will probably have to rewrite your code, unless you're a really veteran designer who's been doing this for years and you just see differently than the rest of us. The guideline is really simple. Sequential logic is defined within simple always at pos edge blocks that map directly to standard cells from the library. Everything else, in other words, combinatorial logic, is defined using assigns and always at star blocks. In other words, there is a clear separation between sequential and combinatorial logic. Remember our picture before? We have a flip-flop, we have combinatorial cloud, and we have a flip-flop. Well, this and this, these are going to be in always at pos edge blocks. They're going to be by themselves. They're going to be mapping directly to a standard cell. It's nothing else. We don't want to have any dirt in here. Everything that's combinatorial is going to be in a separate always at star block. There's going to be no logic, or as little logic as possible, but basically no logic inside the sequential blocks. We're going to be able to see our flip-flops, look at them, understand how they're written, and everything else will be combinatorial, which is much easier to look at and debug. Okay? Let's understand this a bit better. So I'm going to go back a bit into something that maybe is not that well perceived to people who are just starting out. And this is from control theory. There is something called state. And what is the state of a system? So a sequential system has state, and state, or at least the way I define it over here, is it's the minimum set of variables that are required to know what all values in the system are. So for example, if this is our circuit, we have an AND gate over here. The state of having the variables A and B is the state of the system, because we know A and B, we know that what the functionality of the circuit is, so we know what Y is. It's an implicit value. We don't need to store Y in order to know what it is, but we do need to store A and B as the state of the system to know what Y is. That's basically what the state of a system is, okay? If we look at a more complex circuit than just this AND gate, a state is the collection of all the registers along with the primary inputs to the design. So I'm leaving out, memory for right now and just using registers as our memory. So the registers that drive the combinatorial cloud, they are the state of the design. So as you see here, these are called S1, S2, S3, S4, and S5. That is the state of the design. You also have to add the inputs. If we look at a truth table, what we're going to do is we're going to be able to take each one of these outputs, F1, F2, F3, F4, and F5, and we're going to be able to write a truth table, such as we probably learned in some really early, digital logic type course, and we're going to be able to map to write a Boolean function of F1, which is this whole thing, as a function of the primary input A and the state of the design S1, S2, S3, S4, and S5. So these are inputs of design, but they're not regular inputs because they're actually driven by registers and not by a primary input to the design. So the state of our system is going to be the values stored in these registers and the primary input. Okay, and that's going to tell us for each and every single value inside the design what it is, because we know what the topology of the design is. We know what kinds of gates are inside here. So just knowing the inputs to the design and the state registers, we're going to know what everything is implicitly. We're going to be able to write a truth table like this for every single value inside. Okay, let's take that concept and look at it a bit further. The entire set of registers comprises the state. In other words, the output functions that we saw before, F1 and F5, they can either be F1 to F5, they can either be primary outputs of the design, so they're the output of the design, and that's fine, but there are very few outputs in the design. You know, a design will have a few orders of magnitude, probably fewer outputs than internal nodes, okay? Or they are inputs to state registers. So in other words, every single net like this, it's going to go, you know, and keep on going downstream through combinatorial logic until it either hits, you know, the output of the design, or it hits the input to a state register where it's going to get stuck until the next rising edge of the clock. But remember that these state registers, right, they are the entire set of registers of the design. So the same register that drives this net is the register that is going to then sample the net on the next stage. In other words, we have feedback over here. So we have our state register that's driving into this combinatorial block, and some of these internal nets in some way, they are going to then be driven back into the inputs of registers, and those registers, because there is only one set of the entire set of registers, are going to be the same registers that drove them. This is a feedback type of a thing. I'm not saying that S1 necessarily is going to drive S1, but maybe S1 will drive S5, and possibly S1 could drive S1 as well. Okay, so this is what our design looks like, and that's really important. Okay, why? Because what we're going to do is, in a certain clock cycle, we're going to have these S1, S2, S3, S4, and S5 values. These are the state of the design. They're going to be driven into the combinatorial block after we settle, you know, our transition through this, and we have all of these output values, these F1, F2, F4, and F2, F3, F4, and F5. On the next clock cycle, they are going to be sampled in here and override the state. So this is basically the next state of the design. And that's what we are calling this. We're calling this the next state of the design. They are these internal values that are used to feed back into registers somewhere over here. Okay? So what I'm saying is that you have to separate the state and the next state. The sequential part of a design is now very clear. It's the set of registers that makes up the state of the design, all of the registers of our design. These registers should be written out clearly, always at pos edge clock or neg edge reset. If not reset, state gets reset state, else the state gets next state. Okay, so what we have, and this is our sequential part. We just described this flip-flop without any logic at all. Everything else is going to be inside this logic. We have this next state, and we have a state, and we have some sort of reset value that's connected here, some sort of a constant. Okay, everything else calculates the next state and is combinatorial. Okay, so everything over here is going to be combinatorial, always at star blocks, right? Always at star case state. It's going to say, what do we have stored in all of our flip-flops over here? That's going to provide us with the value, either the output or the next state value, you know, that's going to come out over here. Okay, so we made a complete separation between the sequential block, the always at pos edge clock, and the combinatorial always at star block. They're completely separated. There is none of this green is going to seep into this blue, or else it's going to cause us lots of trouble about understanding something. However, I need to make a note that, again, makes people kind of confused at first, and it's a note about state machines. Okay, we need to differentiate between the state of the design, which is what I've been discussing in the last two slides, and the states that make up a finite state machine, an FSM. Okay, the states of an FSM are a really good design tool for creating sequential logic. This is something that I showed in the lecture, right? We can use an FSM to then turn it into real easy Verilog and write our design. It's a really nice tool. But the states of the FSM are not the entire state of the design. The states of the FSM are a very small number of the entire registers of the design. And we said the state of the design is all of the registers of the design. So you have to differentiate between the two things, even though we call them the same thing. In fact, we usually call this small subset of the entire state of the design, we'll call it state, you know, reg state. That's what we showed show in all of the examples, because it's talking about the state of the state machine. But there are a lot of other registers that are the state of the design. Okay, so if we take our simple counter from the lecture, we had 4 states over here. States: idle, count up, count down, and overflow. And for the 4 states that we had in our design, we need, 4 registers if you use one hot encoding. So we have 4, our FSM state just needs 4 registers to give us this S1, S2, S3, and S4, which are the inputs to, our case statement, which decides on our next state logic. However, if we look at this simple example, we also have a current counter value. We had this count up, up, and count down, down, and so forth like that. We need to store maybe 32 bits or 8 bits or something like that for the counter. They are registers, okay? They are registers, and therefore they're part of the state of the design. The counter does do something. In fact, it's inputs into, deciding if we're going to be overflowed or whatever. Okay, so this is part of the state. It's not part of the state registers that make up the FSM, but it's part of the state of the design. So everything we discussed in the previous 2 slides about state in general and how our machine is built, it includes these 4 registers and these 8 registers, not just these 4 registers. And don't get confused about that. The state of the design is all of the registers in the design, and these guys as well. They should be described independently without any logic in them. So I'm going to go back and fix kind of a sin that I made. Okay, in the example code, I cheated and put some logic in the count register sequential block, and this was really simple logic. And don't do it until you're a veteran designer. So it's something you might want to do when you're a veteran, because it makes your code a bit shorter, a bit cleaner. But at this point in your careers, and probably is good practice forever, never do it. It makes things harder to debug. It's much more of a point where you're going to run into errors. Okay, so what we had here was always a positive clock or negative reset. If we are in reset, count is going to become 0. Else, then we started if state is count up, then we should add 1 to count. If state is count down, then remove from count. That is combinatorial. That is logic. We don't want to do that. That's something we don't want to do. Okay, we want to have this thing only map directly to a flip-flop from the standard cell library, and we don't know how to map this part into a flip-flop from a standard cell library. We need to put an adder over here, and maybe some sort of muxes or something like that. Okay, so I'm going to rewrite this now and show you how I should have written it according to the Avada Kedavra rule. Okay, what we're going to have here is always at positive clock or negative reset. If reset, count gets 0. Else, if count enable, then count gets next count. Does this map directly to a standard cell? The answer is yes, because there are enable flops in the counter in the standard cell library, and that's fine. Okay, then we're going to have always at star begin. We're going to first of all reset over here, give a default value, next count equals count. Then we're going to say if state is count up, next count gets count plus 1. If state is count down, next count gets count minus 1. So it's the same thing over here, but we're putting it now in an always at star in a combinatorial block. Okay, and we're going to create this count enable that says if we're in state count up or count down, count enable is going to be 1, if not 0. So the 2 things that I pointed out over here is that we initialize next count, then we don't have to worry about latch inference. Okay, and the other thing is that we can use, we're even encouraged, I mentioned in the lecture, to use load enable flip-flop. So it's a flip-flop with an enable over here. And this is a standard cell. So this is not considered logic inside our sequential block. So this is something that is actually worth using. One of our final things over here is make sure that you do not cause multi-driven nets. So this is another problem. It's another Avada Kedavra. And don't worry, your RTL won't work in any case if you do this. So never assign a signal from 2 always blocks or assigns. Okay, this results in 2 logic blocks that are driving the same net. So we said, always at we said always at star x equals blah, blah, blah. And then another always at star x equals blah, blah, blah. So one of them was describing this function, and one of them was describing this function. Or if I said assigns over here, so assign x equals blah, 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 and then another line saying assign x equals blah, blah, blah. So this is making two functions, and we're actually shorting the output of them. And we know that with CMOS, we cannot deal with that. If you follow the guidelines, which are separating, the combinatorial and the sequential blocks, which I previously called the Avada Kedavra rule, right? It's easy to check this. Each register should have its own always at pos edge block, okay? You can combine several registers into an always at pos edge block, but even really better practice is give each register its own always at pos edge block, and then you don't have this problem. It's really easy to see that this register, you can do a find, and you see that that register is on the left-hand side only in its own very clear always at pos edge block. Signals can appear in the left-hand side of only one always at star block. So again, you look for the signal name, and you'll see it will appear only in one always at star block. And then again, signals can appear on the right-hand side all over the place. You can use signals as an RHS value in many always blocks all over the place. Okay. However, you have to watch out for combinatorial loops. So if for some reason, okay, you have an assignment, a left-hand side over here, that is downstream combinatorial from its own value in the right-hand side, that makes a combinatorial loop. We don't have any registers in here. We have a free-running oscillator, right? The electrons are going to be running around here, and nothing's going to stop them. And this is a really, really bad situation. You can only do this type of feedback if you have a register in the middle, okay? So this is really hard to make sure that you don't do. So make sure you don't have this. It's a combinatorial loop. You will get warnings and so forth all over the place. Sometimes the synthesizers and so forth will error out even depending on the settings you put on. But this is really not going to work in any case. So just to summarize this, after writing your code, go over this simple checklist and make sure that all of this is what I do when I check my students' work, just to make sure that they don't have, they didn't do anything wrong. Okay. Clock and reset signals do not appear on the right-hand side of any always at star or assigns. That's our first rule. Okay. No clock domain crossing occurs. That's also part of our first rule. Okay. All combinatorial ifs have a corresponding else. All case options are covered, and or a default case is provided. And all LHS and if-else case are assigned for all conditions. Right. So that was our second rule. Okay, an LHS in an assign always star are an LHS only in that block. That's what we just said over here as well. Okay, all combinational sensitivity lists use the always at star notation. All sequential blocks have pos edge clock or neg edge reset notation. And no logic in sequential blocks, i.e. always at pos edge blocks map directly to a flip-flop from the standard cell library. Finally, check combinatorial loops so that no left-hand side is affected by itself in the right-hand side, even upstream. And another few additional useful tips that can go a bit beyond this lecture. So you can use System Verilog. System Verilog is a kind of a next generation of Verilog. It's been around for a long time, but it took a while for all the EDA vendors to really support it. But now it's pretty commonplace all over the place. Even if you're not using System Verilog for your verification, you can still use it or use some constructs from it for writing your RTL. And they actually tried to solve this problem of the reg and wire, which drives everybody nuts, by making a single unified type, which is called logic. So instead of using the wire and reg types, use logic type. It's much more clean. Okay. The other thing is that the always blocks, in order not to have these problems of, this notation of pos edge clock and neg edge reset and star and so forth and so on, they changed it to we have these always blocks that are called always comb, which is the same as always at stars. And it also verifies that you never have any multi-driven. So this will be actually verified in your syntax checking. And always FF is instead of using always at pos edge. There's also like an always latch if you really want to latch, but this ensures that you didn't forget that pos edge keyword and that you accidentally created a latch instead of a flip-flop. Initialize your left-hand side values. So that's what we said before. Put an initial value for each left-hand side assignment in an always at star block, and always use a default case value. And it's really worthwhile to run a linter. Now, a linter is a tool that's usually sold kind of separately and runs on your RTL. The problem with linters is that they tend to spit out a lot of hints that say, you know, a lot of things are wrong, and it's sometimes hard to see the trees in between, you know, the whole forest or whatever, or see the forest between the trees, right? It's hard to find your actual mistakes in a linter. But when you run synthesis, it runs some sort of linting, and you see a lot of the types of mistakes, like you'll see latch inference and combinatorial loops and so forth. So it's always worthwhile for even an RTL designer to run synthesis. So that's all I had to say, and I hope that helps you improve your RTL writing and make things work better.